In this video, I'll discuss cosine similarity. I'll talk about the intuition behind computing cosine similarity, followed by the equation for doing so. Then I'll show a case example to illustrate what it looks like in practice. So we've learned now how to create a basic vector space model. However, a vector space model is only useful if you're able to leverage it to determine meaning, and in doing so determine semantic similarity between words. A popular method for computing semantic similarity is cosine similarity. Cosine similarity differs from the other similarity metric we learned earlier this semester, edit distance, because it focuses on differences in meaning encoded as dimensions in word vectors, as opposed to lexical differences like character insertions or substitutions. Cosine similarity is based on the dot product from linear algebra, and in case it's been a while since you refreshed your linear algebra skills, I've included the equation here. Assuming you have two vectors v and w of the same dimensionality, for each dimension I, you just take the product of v sub I and w sub I, and then you sum up all of those products. In doing this, similar vectors, or those that have large values in the same dimensions as one another, will end up having high similarity values, and dissimilar vectors, or those that have, for example, values of 0 in different dimensions from one another, will have low similarity values. Cosine similarity is more than just taking the dot product though, because if we just take the dot product, we would end up with deceptively high similarity values for frequent words. That's because frequent words naturally co-occur with more words than infrequent words, and thus would naturally have higher co-occurrence values with most words in raw form. We don't want that though because it adds noise. Instead, we want our similarity metric to tell us how similar two words are regardless of their frequencies. Frequent words would in general have overall higher length vectors since they have higher values in most directions. So cosine similarity addresses this issue by normalizing the dot product by the vector length. So then we end up with a nice tidy equation that looks like this. In the numerator, we have the dot product between the two vectors v and w, and in the denominator, we have the product of the two vector lengths. The resulting value will range between 0 and 1, with a cosine similarity of 1 meaning that the vectors are identical to one another, and a cosine similarity of 0 meaning that they're orthogonal to one another. So now that we know the equation, we can work through an example to see what computing cosine similarity looks like in practice. Let's say we have a co-occurrence matrix here, and the rows correspond to our target words and the columns correspond to the dimensions in our word vector. Basically, for each target word, we have its co-occurrence frequencies with 3 words. So the word vector for unicorn is 44282, corresponding to its co-occurrence frequencies with the words glitter, data, and computer. We want to compute the cosine similarity between unicorn and information. So we think back to our cosine similarity equation and we go ahead and substitute in our actual values. The word vector for information is 5, 3982, 3325, as we can see from the co-occurrence matrix. So we're going to end up computing cosine similarity based on the values shown here. We remember that to find the dot product, we're just iterating through dimensions and taking the product of the values in each of our vectors at a given dimension, and then summing up all those products. So we update our equation here. And then we go ahead and solve it. So we find that the cosine similarity between unicorn and information is pretty low. It's 0.017. So these two words are not very similar at all. And given that information, we decide, how about we go ahead and figure out the cosine similarity between digital and information as well, to see if maybe digital is more similar to information than unicorn is. So we compute that using our same cosine similarity equation. The vector for digital, as we can see from the co-occurrence matrix, is 5, 1683, 1670. We end up with a way higher cosine similarity value. In fact, it's almost a value of 1. So it turns out that the words digital and information are highly similar. So given our 3 words, we've found that digital and information are much closer to one another than unicorn and information.